Vale, pues buenos días a todos y bienvenidos al seminario de nuestro instituto, el IUMPA, y a este semestre que intentamos poner en marcha dedicado a la computación cuántica, en un poco el intento por parte del instituto de que desde los conocimientos de potencial matemático que tenemos aquí podamos mirar a otras áreas que son de interés. En particular, bueno, pues hemos invitado a Ángela Capel, que viene de la Universidad de Tübingen, y ella es alumna y doctoranda de David Pérez y nos va a hablar desde un punto de vista bastante básico de computación cuántica. En el caso particular de nuestro instituto, que tiene una larga tradición de análisis funcional, posiblemente es una de las áreas que en estos momentos tiene mayor conexión con lo que han sido temas clásicos dentro de las matemáticas y en particular el tema del análisis funcional, las tensor norms y otra serie de cosas, de las cuales espero que no nos hable. Pero bueno, ella amablemente aceptó nuestra invitación y empieza este semestre donde espero que todos desde nuestras diferentes especialidades tengamos la oportunidad de acercarnos a un tema que considero que es muy interesante y que tiene un recorrido importante de ahora en adelante. Sin más preámbulos, te cedo la palabra.
Genial, pues muchísimas gracias por la introducción y muchísimas gracias por supuesto por la invitación a estar hoy aquí. Estoy encantada, es un honor poder venir a contaros un poquito de este problema que os voy a presentar y de la investigación que hacemos. Y me parece genial la idea de intentar aunar distintos temas de matemáticas y ver cómo se pueden aplicar para un campo que está tan en auge como la computación cuántica. Así que la idea del seminario que os quiero contar hoy es justo esa, es contaros un poquito cómo todos estos campos se conectan y cómo se pueden utilizar para atacar estos problemas que están tan en auge hoy en día. En principio, lo que os decía, ¿la hago en español o la hago en inglés? Me da igual, o sea... ¿Sí?
¿Es igual? Sí, sí.
¿Es igual? Ok.
¿Sí?
Pero, sí.
Pero un poquito puedo leer, un poquito discurso, no es claro.
¿Hay otra persona?
Pues si queréis entonces lo hago en inglés. Pues más, okay. For me, I think it's a bit easier because some of the things that I'm presenting here, I'm more familiar to talking about them in English than in Spanish, so I guess it's even easier. Okay, so well, let me just tell you in advance that please, if there's anything that is unclear or anything, I'm very happy to take questions at any time during the talk. Okay, so don't wait until the end because I feel it doesn't make much sense. Okay, so what I'm going to do today is start very basic allocating the problem that I'm going to describe here. And this is going to be living in the intersection between three huge fields of science, right? Which is mathematics, physics, and computer science. What we are going to describe today is something that lives, as I said, in the interplay between these three different fields. And, well, we are mainly mathematicians, or we are in an institute of mathematics. So everything that I'm going to describe is how to use mathematical tools to address these problems and tackle these problems and find some solutions. But the problems are going to arise from the fields of physics and computer science. And more specifically, it's something that is going to be living in the interplay between the fields of quantum information theory and quantum many-body physics. So why are we considering this interplay here? This is something that appeared roughly 40 years ago, and it's something that has been evolving a lot in the last few years. And the connection between these two fields is very fruitful because communication channels in quantum information theory have been used to describe physical interactions in many-body systems and the other way around. So when we identify these two different objects, many fruitful things appear here, and there are some tools and ideas that have been explored for communication channels in quantum information theory that have been used subsequently to solve problems in quantum many-body physics, and the other way around. Some models of quantum many-body physics have been used to construct models of storage and transmission of information in quantum information theory. So this is why we are going to be playing all the time with the interplay between these two things. And in particular, Perdón,
es que me están diciendo que no estoy en YouTube.
Gracias.
Para que tenga más audiencia.
Se agradece.
Va perfectamente.
Perdón.
No, I mean...
A ver si no están mirando que entren en la página del IUMPA.
Vale.
Y ahí debería estar. IUMPA UPV, con guión bajo.
Sin problema, si hay algún problema me dicen. So in particular, I just want to briefly tell you here what we are going to be talking about. So the field of study that we are going to be considering today is that of dissipative evolutions of quantum many-body systems. More in particular, what we are going to study is the velocity of convergence of some quantum dissipative evolutions to the thermal equilibriums. So we are only going to study thermal evolutions, the so-called thermal evolutions. And specifically, what we are going to do is provide sufficient conditions that are static and happen on a Gibbs state, which imply the existence of a positive Sobolev constant. And probably right now, Gibbs state sounds a bit magical to some of you, and Sobolev constants as well. So what I'm going to do is go back now, and I'm going to start introducing all these things that appear here so that we all know what we are talking about. And then we can finish the talk discussing a little bit more about this problem and how to tackle it and how to solve it. And the first thing we're going to do is talk about quantum information theory, because I'm not 100% sure that all of you are familiar with quantum information theory. So what I did now is to present some motivation to this field, how this field was created and why it's interesting to study it. And the motivation for the study of quantum information theory is the following. I mean, it arises from trying to answer these two questions. First of all, if we consider theoretical complex quantum systems, can we actually construct them in reality and manipulate them? And secondly, if we succeed, so if we can really construct these systems, what are the scientific and technological advances of doing that? So this is the motivation for the appearance of this field. And the idea now is that we want to do this because we want to compare the quantum world to the classical world and see what are the advantages of just studying the quantum world with respect to the classical one. And the first advantage the first difference that we find is that the quantum world presents behaviors that contradict our intuition. So everything that we see right now here is classical, it's not quantum, because the quantum is very, very small, so we cannot see it. And it's something that contradicts our intuition. And this happens because the quantum world presents certain properties that we are not super familiar with, and these properties have to do with entanglement, superposition, and so on. So this is something that we will describe now. And these properties provide quantum systems with a more complex and richer behavior than classical systems. So in some sense, we can see quantum systems as a generalization of classical systems, at least with respect to information theory. Because the idea is that with quantum systems, we should be able to simulate always classical systems and not the other way around. So in principle, the converse is not believed to be true. It's actually one of the main problems that people are studying right now, to see that actually quantum systems can perform better than classical systems. And this is the so-called, if you've ever heard that, quantum advantage problem. So just trying to find situations in which quantum perform better than classical. But also the quantum systems present a problem that classical systems don't have, and this problem is called decoherence. And decoherence is a phenomenon that happens in quantum systems, which essentially destroys information very fast. And that tells you that even though you start with a system that is completely different from classical, it becomes almost classical very fast. So that means that this phenomena of quantum that has to do with entanglement and superposition is something that you have to exploit before the information is destroyed. Okay, so this is, in a very high level, the description of why we study these things. And as I said, the main goal of quantum systems nowadays is to be able to control the quantum behavior of scalable quantum systems, so of systems that we can scalate with respect to the size, and achieve the so-called quantum advantage. Okay. And one of the reasons for studying quantum systems, or one of the first applications that appeared when people started studying quantum information theory, had to do with cryptography. And in particular, probably most of you know that the key to the security of public key crypto systems has to do with the fact that it should be difficult to invert the encryption stage, if only the public key is available. This is why all our transactions online are secure. And you just using classical computer, we know that inverting this encryption stage of RSA, which is used for all the transactions that we are using online, for example, for banks or whatever, inverting this inversion stage is a problem that is closely related to the problem of factoring numbers. And that's very good, right? Because factoring numbers is very difficult with classical computers. However, for some reason, this is not working. Thank you. However, as I said, the security of RSA comes from the belief that factoring numbers is hard with classical computers, but for quantum computers is not the case. And this is because Peter Shor, roughly 40 years ago, created this algorithm that is called Shor's factoring algorithm. That is something that I'm not going to describe here, but it's based on the so-called quantum Fourier transform. And essentially, if you grab a number and that you know that you can factorize it to 2 primes, for example, the idea is that this algorithm allows you to factor it in a very efficient way. And that's pretty problematic, because if we consider now a number that has 193 digits, and we want to factor it with a classical computer, it would take roughly 30 CPU years, which is quite a lot, but it's still something admissible. So you could do that with a classical computer, more or less. But with a theoretical quantum computer, with many qubits, it should take roughly 0.1 seconds. So that's pretty bad, because you will be able to factor it too fast. But still, as I said, 183 is still more or less fine. The problem is when you go to 500 digits, for example, this would take a classical computer something that we cannot wait, because 10 to the 12 CPU years is too much. But for a quantum computer, this would be roughly 2 seconds. So that means essentially that with a quantum computer, we would be breaking all RSA and all cryptography and everything. So this is one of the possible applications of quantum information theory and quantum computing, and this is one of the problems that is being explored in the past few years, and at the same time alternatives to this are being explored as well to be resistant against quantum computers. And here I just want to tell you a little bit about the notation I'm going to be using from now on. So in quantum information theory, bracket notation is standard and is due to Paul Dirac. And the idea now is that I'm going to use this notation to denote a vector and this notation to denote a dual vector. And we are just using this inherited from the fact that you can denote the inner product in Cn like this. So you're just separating the vector and the dual like this. And then if you put them in the other position, you are just creating rank 1 operators. Okay, so this is just to introduce the notation that we are going to be discussing now. Because what I want to do now is present you what a qubit is. And a qubit is essentially a quantum bit. So we know how computer science works classically, how computers work classically. They are based on the use of bits, and each bit takes either a 0 or a 1 as a value. And the idea of a qubit is that it's going to take a superposition of the 0 and the 1 at the same time. So formally, a qubit is a system that is described by a 2-dimensional Hilbert space. So you can just think of it as C2. And in C2, we can take the canonical basis or the computational basis and denote it by the ket 0 and the ket 1. And the ket 0 is just going to be the vector 1, 0. And the ket 1 is just going to be the vector 0, 1. So it's just the 2 vectors, right? And essentially, a qubit is going to be an element in the unit sphere. So it's going to be a combination of these 2 vectors, where the coefficients are complex in general, and their modulus squared sum up to 1. Okay, so just an element in the sphere. And this is a qubit in general. And this is the basic unit to measure quantum information. So, as I said, the possible states of a bit are 2, but now the possible states of a qubit are in principle infinite, because it's any element on the sphere. And theoretically, this is why people started conceiving quantum computers as an alternative to perform many more operations than classical computers, because theoretically, if you consider now just one element, just one bit, then the classical operations that you can perform with one bit are 1, so it's just one operation, because your bit takes the value either 0 or 1. However, the quantum operations are 2, because you are just sending the information 0 and 1 simultaneously in a superposition with some coefficients a0 and a1. That means essentially that now if we, instead of taking 1, take 2, then classical operations, like classical information that we are sending with 2 bits, is 2, because we can send either 0, 0, 0, 1, 1, 0, or 1, 1, but it's just one of the 4. However, quantumly, we are always going to have a superposition of the 4 of them, or we can have a superposition of the 4 of them. So that means that with 2 qubits, we can send 4 pieces of information simultaneously. And of course, with these small numbers, this doesn't create a huge difference. But now, if we go to a system of many, many qubits, there is a huge difference, because now, with n classical bits, we can perform n classical operations in parallel, but we can perform 2 to the n quantum operations simultaneously as a superposition of all of them. And you see here that the growth from this n to this 2 to the n is exponential. So essentially, a theoretical quantum computer should give an exponential improvement in the amount of operations performed in parallel compared to the classical computer. Okay? And this is what is usually called an exponential speedup. So of course, this is what now people are trying to achieve with the devices that are being implemented everywhere. I mean, you're probably reading about that in the news. This is purely theoretical. I mean, it's not so easy in practice to achieve this exponential speedup. And as I said, this is something that is a huge problem nowadays, to really understand if this is what happens in reality or there is just some improvement, but not exponential like this one. But this is how the theory is starting. And now, the last thing of introduction that I want to give you about quantum information theory is that, well, I'm going to be talking about Hilbert spaces later, about matrices and everything, and I want to tell you why. And the reason why I'm going to be talking about that is because there are some laws, there are some postulates of quantum mechanics that I believe, and many people believe, and what we do essentially is just use them as the mathematical formalism for everything that we describe later. And the first postulate tells us that given an isolated physical system, there is a complex Hilbert space that is in general separable, so it doesn't need to be finite dimensional, but here I'm going to restrict to finite dimensional for simplicity. And this complex Hilbert space is associated to it, and it's called the state space of the system. And now, for this physical system, every time that we want to describe some property of the system, we describe it with a so-called state vector. And a state vector is nothing but a unitary vector in the state space, okay? Just a unitary vector in this Hilbert space. So this is the way to describe isolated physical systems. And now, once you have an isolated physical system, you want to see what happens to it. So there are 2 possibilities. Either you let it evolve, or you measure it. And the idea of measuring it is that, as I said, physical systems in general are going to be a superposition of different states. But when you observe the system, you have to measure it to obtain one of these states in the superposition with a certain probability that is given by these coefficients here. So first, we are going to see what happens when we just let it evolve. And the way to let it evolve is described, or this evolution is described by a unitary transformation of the Hilbert space. So in this particular case, in which I'm only talking about finite dimensions, this is just a unitary matrix. So if our system in time t1, is given by the state phi1, and at time t2 is given by the state phi2, then to go from t1 to t2, the only thing we have to do is apply a unitary matrix. Okay? And we are just sort of rotating our vector. This is the way that an isolated physical system evolves. And now, as I said, the next thing we have to do is measure it. And the way to measure it is by means of something that is called a quantum measurement. And a quantum measurement is just a collection of operators, in this particular case, a collection of matrices. In general, it's just a collection of bounded linear operators, denoted by Mn, that verify this condition here. This Mn star is just the adjoint of Mn, so we just take the adjoint, multiply with the initial state, and when we sum all of them, they sum up to the identity. Okay? And when they verify these conditions, what we do with them is essentially create a way to obtain different probabilities. So when we measure our system, we want to see whether it is in one of the possible states ranging from 1 to n. And the index n obtained here is just telling us in which of these states our system initially was. And the probability that we obtain such specific state n is given by multiplying are a system that is in state phi with this expression, with the element from this measurement mn star mn, this is the probability that the outcome n occurs, and the state that we obtain after the measurement is given by this expression here, which is just the matrix mn applied to our state phi and normalized with the square root of the probability. Okay? So this is just the way in which you go from the superposition to one specific state that now is going to be classical originally. And finally, everything that I'm telling you here is for an isolated physical system. But what happens when we have several systems and we want to compose them together? And this is something that we do with the fourth postulate. Given a composite physical system, the idea is that now we can model it just by taking a tensor product of all the Hilbert spaces associated to each of our different components. And therefore, the state in which our composite system is going to be prepared is just the tensor product of all the states that are modeling each of our different systems. Okay? So with this these are the only tools that we are going to need related to quantum information in this talk. And here I included this slide. Probably you're familiar with tensor products, but I wasn't sure about the audience. So just in case, I included how a tensor product of vectors happens, and tensor products of matrices. And one important thing here is that I'm going to be talking all the time about sub-regions of lattices, which means that if you consider just a system that is bipartite, like here, in principle, it's completely different to just talk about a density matrix, about a matrix for our system A, or a matrix for the whole system AB, because in particular, if you look at them, they have different dimensions, right? Because the space associated to A and B has double the dimensions, so that means that the matrix should have double the dimensions in both directions. When we want to compare all these matrices, what we have to do is always tensor with identity, so that we increase the dimension of the matrix, and then everything is well defined. So this is just to tell you that every time that I have a matrix that is only living in A, so it's just a bounded linear operator in HA, then we can view it in the global Hilbert space just by tensoring with identity. Okay, and with this, I want to go to the second part, because if you saw the title of the talk, the title was essentially the question that I'm writing here. And this question has to do with quantum many-body systems. So I told you at the beginning that this problem is at the interplay between quantum information theory and quantum many-body systems. And now I want to tell you about quantum many-body systems, because I already told you about quantum information theory. And in this question, I guess that there are many words that maybe are not super familiar for everyone. So what I'm going to be doing is I'm going to be splitting the question into its different parts, and I'm going to be addressing each of the words separately. So first of all, I want to explain what a quantum many-body system is. And a quantum many-body system is just, for me, a sublattice, a square lattice. So it's a subset of ZD. So it's just, you take the integers, you take the integers, of dimension D, and then you take a finite subset of it that I'm going to denote by lambda, and this is what I'm going to be calling a lattice. And now to every side of the lattice, I'm going to associate a finite dimensional Hilbert space because of the postulates that I just told you about. And for simplicity, I'm going to assume that all the Hilbert spaces are going to be the same, so just C to the capital D. And therefore, the global Hilbert space associated to the total lattice is just going to be the tensor product everywhere of all these local Hilbert spaces. And then now, again, I'm going to be talking about the set of bounded linear operators between this H lambda and itself. And I'm just going to denote it by V sub lambda from now on. So the subindex is just going to be telling me in which region this is living, so in which physical system I'm studying these things. And something that is pretty important that I'm going to be using from now on is the set of density matrices. And the set of density matrices, I'm going to denote it by S sub lambda. And these are essentially the matrices in lambda, which are Hermitian, positive semi-definite, and half trace 1. And the reason that we are going to be working with this is because I didn't say that, but when you go to the postulates, what I presented here is something that is called the Heisenberg picture. So it's a way to view the postulates from the point of view of vectors. But now one can take the dual picture, which is called the Schrödinger picture, and this dual picture has to do with density matrices, and for us it's much more convenient to work there. So, but the idea behind it is exactly the same. So with this, I'm telling you what for me a closed quantum many-body system is. So it's just a set of, a subset of a square lattice essentially, so a subset of set D that has this global Hilbert space associated. It's just that. But now you can associate to this closed quantum many-body system something that is called a Hamiltonian that I will introduce later. And this Hamiltonian can evolve with time, and you can study its evolution, but this is not what we are going to be doing here. What we are going to be doing here is assume that we don't have a closed quantum many-body system, but something that is called an open quantum many-body system. And an open quantum many-body system is something that is in principle more realistic, because now if you try to perform an experiment in a lab, it's impossible to perform it completely at zero temperature or completely shielded from noise. This is something that you cannot have. It's something that you cannot do. And that means essentially that our set of dots that I had before is contained in something larger that is called an environment that is interacting with it, is just bringing to it some noise. So again, the notation is going to be the same, but now the idea is that to our initial system, we are going to give it some energy, or it's going to have some energy, and with time, this energy is going to tend to dissipate. And therefore, the continuous time evolution of this system is going to be something that is going to be dissipative, and it's something that we will be able to describe with a quantum Markov semigroup because of something that is called the Markovian approximation. But to arrive to this Markovian approximation, I want to give you a few concepts before. So, as I said, we are describing quantum many-body systems, and the thing we are going to do now is to see the description of the evolution of open quantum many-body systems. And first of all, to see the evolution, let me remind you that when we were talking about isolated systems, the physical evolution was given by conjugation with unitaries. Because this is what we said in postulate 2, right? That the evolution was given by unitaries. So in particular, if we have an isolated system and we conjugate it with unitaries, we know that this is reversible, because we can just apply the unitaries, or the star and the U here, and obtain back the initial state. However, if we have a dissipative quantum system, we necessarily need to have something that is a non-reversible evolution. This is something that is going to be an irreversible thermodynamic process, and we need to be able to describe it. And first of all, what we need to do is construct a set of operations that let us describe these physical things that are happening to our system, I would say. And we need to think, initially when they were describing this set of operations, they needed to think which properties needed to be conserved in a physical system, so that it's what we have to require from these maps here. And the first thing that we require is that if we take density matrices, they need to be mapped to density matrices. And the idea is that if these density matrices, we view them in classical systems, for example, instead of in quantum systems, this is just a diagonal matrix. And all the entries in the diagonal are just terms that are larger than or equal to 0, less than or equal to 1, and they sum up to 1. So they are just like a probability mass function that you are placing in the diagonal of a matrix. And this is something that needs to be conserved under the evolution of these maps. And for that to be conserved, specifically you are asking for your map here to be linear, positive, and trace preserving. So these are the first conditions that you have to impose there. However, you need to impose something else, which is that now our matrix here is going to be describing some property in our system. But as I told you before, our system is not alone anymore. Our system has an environment in which it is contained and with which it is interacting. However, our map doesn't care about what happens to this environment. And that means essentially that if we take now a modified map that we apply to our state, our density matrix, jointly with the density matrix that is modeling the effect of the environment, then this needs to have trivial evolution under our map. So that means that if now this map needs to be also positive. So when we take the map that is just the part that acts on the system and the part that acts on the environment is just trivial, this still needs to be positive, And in principle, the environment can be as large as possible. So this needs to happen for every possible dimension of the identity. And when this is always positive, for every possible dimension of the identity, this map is called completely positive. So this is how we describe the maps that are going to be describing the dissipative quantum system. They are just linear, completely positive, and trace-preserving maps, and these are called quantum channels. So from now on, every time that I talk about a quantum channel, I'm going to be talking about a completely positive and trace-preserving map. And this is one way, like one naive attempt to describe these kind of evolutions and to kind of justify that we need to use quantum channels for this.
Sorry, what do you mean by positive? Yes.
By positive, what I mean is that maybe it's just that it takes positive semi-definite matrices to positive semi-definite matrices, just that. And there's another way to describe these kind of maps, and maybe it's easier to convince you that these are the requirements that we need to impose so that we can describe a dissipative quantum system. And the idea is the following, okay? Maybe to give you a bit more of intuition of what we are doing here, we have a system that is containing an environment, and this system is going to dissipate energy, okay? So imagine, I like to imagine it classically as a cup of coffee that one has in a room, for example. The cup of coffee is initially very hot, and the temperature of the room is cool, but when you let it evolve with time, after infinite time, there is an equilibrium between the temperature of your coffee and the temperature of the room, right? So the temperature of your coffee decreased, and the temperature of the room slightly increased, but it's something that is not perceptible by us because the room is huge. However, as we are seeing, the temperature of the room is affecting the coffee, and this is why the coffee is getting colder. But if now we somehow could completely isolate the room, and there was no interaction with the outside world, maybe we could see the room and the coffee as an isolated physical system, and we could forget about what happens outside. And this is essentially what we can do now. We can take our system, join it with the environment, and assume that everything together we can put it in a box. And this is now an isolated system. And what I told you before about isolated physical systems is that they are evolved with unitaries. So what we do now is take our density matrix in our system, we put it together with some density matrix in the environment. Now I'm taking it of this form for simplicity. And now we let it evolve with unitaries. But of course we need to see what happens at the end for the system, not for the environment. So we need to get rid of the environment. And the way to get rid of it is just tracing it out. So using a partial trace of the environment out. And then we obtain this final density matrix for the system. And all the maps that I drew here, so all these arrows, are completely positive and trace-preserving maps, like the ones I was describing before. So when you compose all of them, you have a completely positive and trace-preserving map. So this is another way to see that a dissipative quantum system can be modeled using a quantum channel. Okay, so these are the two ways. But of course, what I'm telling you until now has to do with what happens infinitesimally at every instant of time. But now we want to describe the evolution through time. And this is something that I haven't told you yet how to do. So essentially what we have to do is glue all these quantum channels. So until now, for every instant of time, we have a corresponding time slice, that is a realizable evolution, a quantum channel, and we need to put all of them together. And if you try to do that mathematically, you can't. You don't have tools to solve that problem of gluing all these operators together, taking into account the effect on the environment. So now it's when you have to start making assumptions that are physically admissible and mathematically helpful. And these assumptions have to be made on the environment. And the first assumption that we have to make is that the effect of the environment is almost irrelevant, but still important on our system. And we have to assume that the environment does not evolve. And this is something that, in the example of the cup of coffee I was telling you before, is something we can think of if the cup of coffee is very small and the volume is very large, right? So that's something that is sort of unmissable. And this is something that is called the weak coupling limit. So essentially what we do at every instant of time is consider our density matrix in our state, and we tensor it with the effect of the environment, and then after this infinitesimal time, we trace it out, and then we tensor it again, and so on and so forth. But the state with which we are tensoring it is always the same. It doesn't evolve. So this is the first thing that we have to assume. And apart from that, something that also needs to be assumed is even if the environment doesn't evolve, it holds memory with the effect that it has on the state. In principle, it would hold memory on the effect it has on the state, but you have to assume that actually this doesn't happen. So you have to assume Markovianity. You have to assume that your environment holds no memory of what happened in the past, and therefore the future only depends on the present. And this is why this approximation is called Markovian approximation. Okay, because in the end, what is happening here is some Markovian process. So it's the quantum analog of the classical Markov process. And with all these things I told you until now we are in position to describe mathematically the objects with which we describe the dissipative evolution of a quantum many-body system. And these objects are just quantum Markov semigroups, which are one-parameter continuous semigroups of completely positive and trace-preserving maps. So again, everything I'm telling you here is finite dimensional, so you can just imagine that all the maps I'm writing here are just super operators, but they are just maps that you're applying on matrices and output matrices, but all these things can be extended to infinite dimensions without any problem. And it's a quantum Markov semigroup. The Markovian part I already told you. The quantum part just comes from the fact that we are defining these over Hilbert spaces, and the semigroup part comes from the fact that we have these two properties here. So you have a whole family of operators. When you compose two of them at instant t and s, what you get is the one at instant t plus s, and the initial one at instant 0 just coincides with the identity map. Okay, and these are the only two properties that you have for a quantum Markov semigroup. And since we are in finite dimensions, everything works fine. So we can find an infinitesimal generator. That is the infinitesimal generator of the semigroup. And that essentially tells us that if we differentiate the element at instant t, this infinitesimal generator, we have the equation that we have the equality between that derivative and composing with the infinitesimal generator in the left part and in the right part with the instant at time t. And the reason why this is interesting for us is because now we can integrate this equation, which is usually called Liouville's equation or the master equation, and this lets us describe each element of the semigroup at instant t as the exponential at time t of the infinitesimal generator. And this is pretty useful for us to study what happens here. And additionally to this, I don't want to go into details, but the specific form of this generator is given by something like this. This part is the part that describes what happens only in the system, and this part describes the interactions between the system and the environment, which is usually going to be a feedback. And it's called the GKLS equation, and this L is Lindblad, and this is why we also call it Lindbladian. So I'm going to be talking about Lindbladians right now. Okay, so we want to address the question of when does a quantum many-body system mix rapidly? I told you what a quantum many-body system is and how we are describing its evolution. And now I'm going to tell you about what mix means. A mix is just convergence. So when I'm talking about mixing, I'm just talking about convergence of this semigroup. So for our semigroup to be, for us to have the guarantee that our semigroup is going to converge, we have to assume something that is called primitivity. And this primitivity is essentially that our semigroup has a unique invariant state that is going to be also full rank. And we are always going to denote it by sigma lambda. So there is a unique density matrix such that every time we apply any of the elements of the semigroup to it, it's invariant. Okay, it's the sigma lambda here. And once we have this condition, we have guaranteed convergence of our semigroup. And now we also need to assume something else, which is called reversibility or detailed balance condition. And this is essentially telling us that the infinitesimal generator of the semigroup I was presenting before is self-adjoint with respect to this inner product. And this inner product that has a small sigma here is just the inner product that is given by just taking two Hermitian matrices and taking the trace of one and this weight to the power 1/2, and the other one and the weight to the power 1/2. Okay, this is called the KMS inner product. And when our infinitesimal generator is self-adjoint with respect to that, we have this detail balance condition. And once we assume these two properties, we have the following. We take now any density matrix on our system that is modeling some property there. We let it evolve with time. So after a certain time t, its state is given by the element t of the semigroup applied to it. And let me just denote it by rho sub t. And then that means that after a certain time t, our element is given by the exponential with time t of the infinitesimal generator and this state rho lambda. And when we let time evolve to infinity, this is always going to converge to the fixed point, which is this state sigma lambda that I was describing here. Okay? So this is why in the question I'm saying when does it mix rapidly? Because if it was just when does it mix with the assumptions that we are imposing, it mixes always, right? So it converges always. But now the important part is how fast does this convergence happen? And how fast is given by the mixing time of the evolution. So first of all, I can define the mixing time of the semigroup as the minimum instant after which, if you take the evolution of any density matrix after that time, it has already fallen inside the ball centered in sigma and of radius epsilon. So this is how you describe the mixing time of the semigroup. And this sigma here, since I said that is the unique fixed point, this is why this T infinity of rho, it always coincides with sigma, okay? So when you do that for any possible initial density matrix in your system, and you take the supremum over it, this is how you describe the mixing time of the evolution. And what I'm going to call rapid mixing is just going to be that the epsilon that I write here is something that decays exponentially with time and scales polynomially with the size of lambda, so with the amount of sites that we are considering in our lattice. And this is something that it's important to understand what it means. So the important part is not the exponential decay with time, because this is something that is standard to show for this kind of evolutions. The important part is the polynomial scaling with the system size. And now let's go back to the motivation of what we are trying to describe with this. These lambdas are going to be the qubits that we are going to put in a quantum memory, for example, and we are trying to build this quantum memory in a lab. So this is essentially telling us that if we put one more site to our system, this quantity is not going to increase a lot. What is sort of easy to show in general is that this is going to scale exponentially with the size of lambda, but that would provoke a very unstable effect, I would say, when adding a bigger number of qubits to our memory, to our device. So this is why we are interested in the case in which this is sort of controlled by something that is smaller. And this smaller is given by just this polynomial on the system size, okay? So from now on, I'm just interested in this rapid mixing property. And well, as you can imagine, given by the expression that is given, which is the supremum of this quantity here, it's something that is very difficult to prove in general, because this is supremum over an infinite amount of density matrices, so it's very difficult to really show that this happens. So what we have to do is find some sufficient conditions that imply that this condition holds. And this is what we do from now on. But before doing that, because that's going to be the most technical part, what I want to do is tell you why we are interested in these kind of things. So now we are going to change, and there's going to be very little of mathematics, and there's going to be a lot of selling while we are doing this. And the idea is that we are trying to construct a quantum computer. I mean, we are not, but some people are trying to construct a quantum computer. And one of the problems that appears when trying to construct a quantum computers is the appearance of noise. So there's this noise in the environment that is affecting the systems that they are creating in labs, and is destroying the information too fast. So first of all, some of these kinds of noise can be modeled using our quantum dissipative evolutions and quantum Markov semigroups, which means that all the information that you can obtain mathematically about them is going to be good for these people in the labs. So this is one of the reasons we work with them. So this, when people in labs started working on this and they started seeing these kind of problems, at the beginning, well, it was like a huge problem that the information was destroyed too fast, so it was very difficult to really scale this system so that they could really do what they should do for long periods of time. However, a few years ago, there was a change of perspective in how to tackle this problem. And instead of seeing it just as a problem, how noise destroys information, it was seen as a resource to exploit for protection of operations, for example, or these kind of things. So this is why a new area was created, something that is called quantum dissipative engineering. And in this area, the main purpose is to create artificial evolutions in which the dissipative process, instead of working in the direction of destroying the information, works in the direction of protecting the system from noisy evolutions. And here, many problems appeared, more or less at the same time. Of course, some of them have to do with the computational power of this branch, on the conditions that one has to assume to have a system that is resilient against noise, or on the time to obtain certain states, which is essentially the direction in which we are working here. And more specifically, the idea is that if we have this property of rapid mixing, what we are trying to prove all the time, what this is telling us is the following. If now we are modeling with our quantum Markov semigroup some noise that is appearing in the physical system, then there is a negative point of view that is happening there. This negative point of view is that usually, if you have a quantum circuit, what you are going to do is start it with a ground state of a Hamiltonian. So you're going to have your Hamiltonian describing the system. You're going to start it with the ground state, for example, and if you let it evolve, this is going to converge to the Gibbs state at a certain temperature. And in principle, this Gibbs state and the ground state, I will tell you about Gibbs state later, these things are usually very, very different, and they have very different properties. And that means that if we let this evolution evolve with time, after a very short time, we're going to be very far from the initial properties that we had there, and very close to the properties of the Gibbs state, and that's something that we don't want for some purposes, like some that I'm going to tell you now. However, if instead of seeing it from the negative point of view, we see it from the positive point of view, we have the opposite. Yeah.
This formula that you're writing for the supreme.
Yes.
Okay, you mentioned about the importance of the scaling of with lambda.
Yes.
But what about the gamma?
The gamma is actually going to be pretty important. It's going to appear later, because this gamma, the role that it has is going to be played by these log Sobolev constants that I will introduce later. And what you can prove there is that as long as you can compensate the effect of the gamma with the poly of lambda, you are fine. So for us, this gamma can be as bad as something that is polylog with the system size, so that you can compensate this effect here. So gamma doesn't even need to be a constant. If it's polylog, it's still fine. So at least you can have that.
This would be also a limit from the other side. There is,
Sorry?
So there should be a limit from the other side. There is a column, like.
Yes, but it's very difficult. Like a limit from the other side is very difficult to prove in general as well. Suppose you can like lower bound everything by zero and everything, but it's very difficult to. I mean, okay, this is something that I will show you now in a diagram that I will show in a few slides. But it's a very good point. But I will go back to that. So just before going back to that, as I said, just from the positive point of view, since this semigroup is going closer to the Gibbs state very fast, that means essentially that if the task you're performing with your quantum circuit is that of preparing Gibbs states, then you are in a very good track, right? Because you're very close to the Gibbs state pretty fast. So that means essentially that Gibbs states or thermal states with short mixing time can be constructed efficiently with a quantum device that simulates the effect of the thermal bath. And this has many, many different applications in different optimization problems that have to do with simulated annealing type algorithms and everything. So I don't want to go into details here, but just to say that this kind of explorations has many positive applications. And now for the negative point of view, I want to talk about error correction. I'm not going to talk about the details of error correction, but just to say that what we do here can be applied for error correction in the following way. The idea is that of how a quantum device should work is that you have some initial information that you store there, and this, you know that after a certain time is going to be destroyed little by little. So you should be able to implement some sort of error correction that corrects the errors that are generated with time, and that corrects them faster than how your noise is destroying the information there. However, the general belief of people working in error correction is that the mixing time of the evolution should be exponential with the system size, so that self-correction is possible. That means essentially if it's exponential, it's something that is very big, right? So the error is being, the information is being destroyed slower, and that means that you have time to implement some codes in your system that self-correct these errors. Maybe you don't need so much. Maybe you can even use some external aid to correct these errors, and this is just what is general error correction. But even for that, people working on error correction tell us that you will need some mixing time that scales polynomially with the system size. However, our mixing time scales polylogarithmically with the system size, because the mixing time is now given by polylog with the system size. That means that if we have rapid mixing, it's impossible to have error correction. So therefore, what we are doing now is use our results, in which we prove rapid mixing, to discriminate systems for which systems that you could use for quantum memory devices. So essentially, what we are doing is taking a Hamiltonian that is believed to be useful for error correction, to be used as a quantum memory device, and then we are constructing the Gibbs state with the Hamiltonian, and we are seeing whether we can prove rapid mixing or not. And if we can prove rapid mixing, then we are essentially saying, no, this system is bad, so don't use it for quantum memory. Okay, so this is how you can apply these purely mathematical results to say something about quantum memories, which is going in the bad direction, I know. So it's not telling you this is good for a quantum memory, it's more in the discriminating side. But we would like to be able to reverse the cycle in the future. And there are other many possible applications of rapid mixing, which I'm not going to describe here. They have to do with some more theoretical results, also with some other error correcting codes that you can implement that have to do with optimized Markovian noise models. And they also have to do with preparation of Gibbs states, as I said before, and mostly with the study of different phases of matter, which is something that is pretty interesting, I think. So if you just think of the usual phases of matter for water, for example, that we all know, the three possible different phases of matter there, this is something that you can also study at the quantum level. And if you just study closed systems in which there's no interaction with an environment, there is more or less a general agreement on how you would describe what a phase of this matter is. But for the dissipative case, so for the case in which you have an interaction with an environment, there's no general agreement for the moment. There are many different ways of describing phases of matter and describing whether there's a phase transition or not. And what we can do is, every time that we show that there's rapid mixing for the whole range of temperatures of a certain system, what we are showing there is that there is no phase transition for this particular case. So just another way to relate this kind of results to physical systems. And since I don't want to take much more time from you, I think I'm going to briefly tell you this part of when does a quantum many-body system mix rapidly. And I'm just going to give you some very few details about this. And if anyone is interested, we can keep discussing later, of course, but I guess I shouldn't take much longer. So the idea to address this question of rapid mixing is that, as I said, it's very difficult to predict ad hoc. So what we do is to find a sufficient condition that implies it. And this sufficient condition is something that is called a modified logarithmic Sobolev inequality. So this is where the more analytical part is coming into play. And the idea is that before we had the master equation that was given by this expression here. Now I'm just changing the notation just by writing rho t everywhere. And we consider a way to measure how different two density matrices are. And this way is called the relative entropy of the two density matrices. So this is just given by the trace of one of the density matrices and the difference between the logarithms of the other two. This, if you know something about the curve linear divergence in classical systems, this is just a quantum generalization of that. And now we can study what happens to this quantity. This quantity is always larger than or equal to 0. And it's only equal to 0 if and only if the two elements that appear here are the same. And that means essentially that we have a function of time that is larger than or equal to 0, and it's going to go to 0 in the infinite limit. So it's something that if we draw it, it's going to be something like this. When we let time evolve, it's going to go to 0, it's going to be decreasing. And that means essentially that if we now take the derivative with respect to time, the derivative is always going to be negative, but its modulus is also going to be decreasing, the same as the relative entropy itself. And this gives us the possibility of constructing something that is called a functional inequality, which is something in which you can relate the relative entropy between these two density matrices with minus its derivative, because now minus the derivative and the relative entropy itself, both of them have the same sign. So of course, for every density matrix rho and for every instant of time, you can find a positive constant alpha such that this is true. Another question is, can you find a universal alpha that you can put here always such that this inequality is always true? And if the answer is yes, I mean positive, so it shouldn't be 0. And if the answer is yes, then you have a modified logarithmic Sobolev inequality.
Yes. That's what I said. So rho T is the reduced density matrix of the system like T.
Exactly.
Or is the system plus environment?
No, there's no environment for the moment. Yes, that's a good point. There's no environment for the moment. It's just the system, yes.
It's a mixed state.
Yes, exactly. Yes, good point. So if this happens, then we have a modified logarithmic Sobolev inequality. Sorry.
Because and then the master equation if there is no environment, which are the Liouvilleans.
You take, yeah, it's a good point. I mean, you take the so the Liouvillean actually has the part of the environment, but you are tracing it out. So something that I didn't write when I wrote before. When I wrote it before, I wrote it for the Heisenberg picture and not for the Schrödinger picture. For the Schrödinger picture, I should trace out the effect of the environment. So of course, the Liouvillean has some effect with the environment. That's completely true. But you have to trace out the effect. Exactly. So you have the same dimensions. So exactly, you're completely right. Yes. And the natural candidate that you would put here would be just the infimum of taking the quotient between the right-hand side and the left-hand side. So this is how we define the modified logarithmic Sobolev constant, so the MLSI constant. And now, something that I'm kind of hiding under the carpet is that I'm telling you that if this is positive, then we have an MLSI. And if you take a look at all the quantities that I'm writing here, and you start assuming some standard conditions on the Lindbladian, it's kind of easy to see that this term here is actually always positive, because the kernels of the numerator and the denominator coincide, and one can show that since here the infimum is taken over a compact because we are just taking here a finite dimensional Hilbert space, this infimum can be written actually as a minimum, and this minimum is always going to be attained. So this is actually going to be always positive. So then you will be saying, okay, you always have an MLSI, and then we are done. No, the answer is no, because what we are interested in is not the fact that the MLSI constant itself is positive, but that the fact that when you take now an increasing family of lattices going to the so-called thermodynamic limit, which is the whole lattice set D, that this is still positive. And this is something that is very difficult to prove in general, because in general, this quantity here is going to depend on the size of lambda. And of course, now if you take the size of lambda to go to infinity, this is usually going to go to 0. We are not even completely assuming that this is strictly positive, but as we were saying before, that this is scaling logarithmically with the system size, but we will go back to that. But if this happens, what you can do now is go back to this inequality here, to this differential inequality, and integrate it using Grunwald's lemma, for example, and then you obtain some inequality like this one. And if you put it together with Pinsker's inequality, you obtain what I'm writing here. So Pinsker's inequality is given by this expression. That means essentially that we can upper bound the one norm of the difference between two states by something depending on the relative entropy, as we do here. And now if we put it together with this inequality, we obtain this expression. So now we have a square root of the relative entropy with a factor 2 and this exponential decay with time. And now we see when the relative entropy is as big as possible, and that happens when the first density matrix is a projector onto the subspace spanned by the minimal eigenvalue of the second density matrix. And in that particular case, the value of this is the logarithm of the inverse of the minimal eigenvalue of that matrix. In that particular case, you obtain some expression like this. And if you remember the expression that we had for rapid mixing, which was something that for which this one norm scaled polynomially, well, could be upper bounded polynomially with the system size and decayed exponentially with time, then when this scales polynomially with the system size, we are done. But in the particular cases we are studying, which are these Gibbs states or these thermal states of local Hamiltonians, this is going to be the case. In this particular case, the minimal eigenvalue can be shown to scale like inversely with the exponential of the system size. And therefore, in all these cases, we are always going to have that an MLSI implies rapid mixing. Okay, so now my problem of studying when we have rapid mixing has been translated to the problem of studying when we have an MLSI. Okay?
Sorry?
Yeah.
I have a question.
Yeah.
So how high is the Pinsker inequality? Because as far as I understand here, so if we use a different inequality, we may have a different bound.
Yes. Yes. So actually, that's a very good point. It's known not to be tight. It's not known to be tight. You can change the 2 by square root of 2 by a factor square root of 2 in general. And in that particular case, as far as I know, it's not clear whether it's completely tight or not. But in general, what you cannot change is the order. So the square, you cannot change it by some smaller power, or at least there's no evidence that you can do that. So, but yeah, I agree. Okay, so as I said, to the question, when does a dissipative quantum mechanical system mix rapidly? The answer is when we can show that it has a positive MLSI, then we know that it mixes rapidly. And now I want to show you this diagram. I don't know if it's going to be possible to read it from the back, because maybe the letters are a bit small. So just to give you like an evidence more or less of the characters that are playing a role in this game for the moment, we have this rapid mixing that we want to prove. We know that if we have an MLSI, this implies rapid mixing. But there's the possibility of just exploring different forms of functional inequalities, which is what people initially did for classical spin systems. And one possible inequality that can be studied here is called the Poincaré inequality, in which you obtain also exponential decays for the relative entropy, but not for the variance. So now you just define the variance, same way that you would define the variance in probability theory. And if you do that, so, well, with this expression here, what this implies is some form of slower mixing, which is something that here scales exponentially with the square root of the system size instead of polynomially. Okay, and this is what is related to your question before. It's not clear what happens here. So in general, you shouldn't be able to go to this from this slower mixing to this rapid mixing, and in general, you cannot go from the Poincaré inequality to the rapid mixing. But there are no explicit counterexamples either in the quantum realm so far, that this is really extremely weaker than this. So it's not 100% clear what happens here. But in principle, what we try to do is create a separation of phases between some mixing time that scales polylogarithmically with the system size and some mixing time that scales like the square root of the system size. Okay, so as I said, the idea is that now, using MLSIs, you imply rapid mixing. Using Poincaré inequalities, in principle, not. So this is easier to prove, but it's useless for us for the moment. But still, proving an MLSI inequality, an MLSI is actually quite difficult, because again, you have an infimum over things, so it's very difficult to derive that. It would be great to have some condition that is not variational, that gives us the same information. And for that, we have to go to the realm of decay of correlations on Gibbs states. And I guess it's a bit late. Can I continue? Or? Okay, great. Then I will tell you a little bit about this, because it's really very interesting to see the connections that appear now. Because now we just go to the fixed point of the evolution, which is just a density matrix there. It's going to be the Gibbs state of a local commuting Hamiltonian. So it's going to be just the exponential of a certain Hamiltonian, well, minus a certain Hamiltonian over its divided by its trace. And we are going to study correlations only there, and just obtaining some static conditions there, so conditions that don't depend on time there. We are going to be able to conclude some things of dynamical processes, because here all these processes have to do with time. And here I give you a small intuition of why we are studying how correlations decay on Gibbs states. And the idea essentially is, probably everybody knows that, of course, if we have an exponential of a sum of scalars, we can split it into the product of exponentials. But in general, if we have an exponential of a sum of operators, we cannot do that unless the two matrices here commute. And actually, there's something that is called the Baker-Campbell-Hausdorff formula, which tells us that if we want to write the product of the exponential of x and the exponential of y, this can be written as the exponential of x plus y, and then a lot of terms that have to do with commutators between x and y. So the idea essentially now is that since we are going to be working with Gibbs states, we are going to have exponentials of Hamiltonians, and our Hamiltonians are going to be sum of terms, but these terms are not going to commute in general, so we are not going to be able to split these exponentials. And this is why I'm telling you about this, because this is what is going to complicate everything for us from now on. And these Hamiltonians, just to introduce them here, for us, they are just going to be some self-adjoint matrices living in, this should be a lambda, living in lambda, which can be written as a sum of local terms, so as a sum of matrices in smaller subregions. And as I said before, we have to take into account that all the dimensions have always to be the same, so every time I'm writing this, I'm tensoring with identity in the complement, so that this makes sense, because otherwise you cannot sum these matrices that have different dimensions. And our Hamiltonian is going to satisfy some further conditions. They are going to be finite range, which means that if our set X is too big, so if its diameter is larger than R, then the term is just going to be 0. So we are only considering interactions that have small support. And we are also going to assume that it's translation invariant. So if we consider as an element of the Hamiltonian that lives in a certain region X, when we translate it over the whole set D, this is going to have exactly the same value. And sometimes we will assume that our Hamiltonian is commuting, which means that every two elements in this sum commute, and therefore here you can actually split these exponentials, but this is not going to be the case in general, so it's just to mention it here. And now with this, we can study this decay of correlations on Gibbs states, and for that we have to describe the correlation properties of Gibbs states of local Hamiltonians. So as I said, a Hamiltonian in lambda, in this lattice lambda, is a sum of terms, and we can in particular write it as the sum of terms that have support completely on this region A, some terms that have support completely in region B, some terms that have support completely in the complement, and then the terms that have support in the boundary of A, so they touch inside A and the complement, and the same thing for B. And we don't have terms that touch both A and B because we assume that A and B are separated enough. And we have finite range Hamiltonians. So. And then the Gibbs state, again, is going to be given by the exponential of minus the Hamiltonian over the trace of it. And you see that there's always a beta appearing, and this beta is just the inverse of the temperature. So sometimes I will mention it, sometimes I will just absorb it inside the Hamiltonian, and then we can forget about it. But just to tell you that this model is the inverse of the temperature. And then there are two fundamental questions here that are essentially describing how correlations decay between A and B. And the first one of them is, as I said, if we cannot split the exponential between these two parts, how far are we from being able to split them? And secondly, instead of just splitting the exponential itself, we consider the normalized exponential over the trace, and we trace out the effect on the complement. So here we trace out what happens outside of A and what happens outside of B, and we see how far it is from tracing out what happens outside of AB. These are two ways of measuring correlations, quantum correlations of Gibbs states. And there are many different forms of measuring them. Here, I just want to mention these three. And I'm not going to go into details because this is probably not super interesting right now. But the only thing I want to mention here is that at least we can establish a hierarchy between these three ways of measuring correlations. We know that one of them, the first one that I'm writing here, is smaller than the second one, and this is smaller than the third one. And that means essentially that now, if we go back to the picture that I was drawing before, we can write the three of them. So since this is the largest one, having some exponential decay here, with the distance between A and B, is going to imply exponential decay in the other two, of course. And something that has been proven in these past few years is that having rapid mixing implies exponential decay of this one, and having a Poincare inequality is actually equivalent to having an exponential decay of this one. So the idea now is, how can you go from this one that is like the strongest one to this other blue box here, blue-green box here? And this is what we explore here in this project. So what I've been working on in these past few years is to go from this mixing condition to this MLSI. Because if you have now this exponential decay of this mixing condition, and if you somehow can reverse this arrow here, then you have a complete cycle in this part of the diagram. And let's think now about what this means. So this means essentially that I was telling you before, if we have rapid mixing, we have a bad material for a quantum memory. That would mean that now, if we have this mixing condition on the Gibbs state that is describing this material, then the material cannot be used for a quantum memory. But we would like to go in the positive direction. So can we actually, given a material, can we say whether it's a possible candidate for a quantum memory? And this is something that we would actually be able to do if we could reverse this arrow here, because then we would have a characterization of when a material is a candidate. That doesn't mean that it's good, but it's a candidate at least to build a quantum memory with it. It would be an if and only if this condition is satisfied. Okay, so this is why we are interested in closing this cycle in this diagram. And secondly, if we could show that this arrow only goes down in general and it doesn't go up in general, then you could establish another cycle here. And that would mean that you have like two different phases. One phase in which you have this rapid mixing, and one phase in which you have this slower mixing, as we were saying before. But of course, there are many things here that are still unknown. And the rest of the things I wanted to tell you now have to do with a strategy, how to prove MLSIs in general, but that is going to take a few more time, so maybe it doesn't make much sense to go into detail now. So, as you wish, I mean, maybe we can finish it like this. So then I will jump to the conclusions directly. Just to say that the two questions that you have to address now are given a local Hamiltonian and constructing a Gibbs state from it, and given a local Lindbladian with unique stationary state as the one I was saying before, this sigma that is this Gibbs state. The questions we are addressing have to do with, first, does this Lindbladian have a positive constant MLSI? And secondly, to prove that, how do correlations between spatially separated regions of the Gibbs state behave? And for this, we create all this MLSI machinery, and it has a lot of pictures, a lot of things. And this is something we can discuss later if you are interested. And with this, I want to tell you the conclusions of what we've been discussing. So what we have been doing is essentially present a problem that lies at the intersection of quantum information theory and quantum many-body systems. And now maybe it's more clear to see why it's at the intersection of that. All the things, all these inequalities for entropic quantities that I showed you to create these MLSIs, which essentially imply rapid mixing, all this machinery are from quantum information theory. This is why you are using tools from quantum information theory to address a problem in quantum many-body systems that has to do with this speed of convergence of dissipative evolutions. And this is why now we have this complete picture of the intersection. For that, we have used tools from many fields within mathematics. So I haven't been into much detail there, but you've seen me mention here inequalities. There are things related to optimal transport. There are things related to probability. The part that I've skipped about the how to prove MLSIs have to do with convex geometry. So there are many different branches that play some important role for all this problem. And what we've done after that has been to discuss dissipative evolutions of quantum manifold systems and their convergence time, this mixing time. We have mentioned possible applications of having rapid mixing in the context of quantum computing, and in particular in error correction. And we have introduced log-Sobolev constants as a tool to prove this property of rapid mixing. And the last thing we haven't done, which is this strategy. And with this, I want to conclude. So thank you very much for your attention, and now I'm very happy to take your questions.
Thank you very much. Questions?
Yes.
In the property that could characterize a memory with quantum memories, okay, you prepare an initial state and then let it evolve and compare the final state with the initial state.
Yes.
And then average the possible initial states.
Yes.
So do you think that both concepts are related?
I mean,
Mixing time with the, there is a figure of memory which is called fidelity, right?
Yes.
It compares this evolved state with the initial state.
Yes.
And this would be, to me, at least naive description of how the memories behave.
It makes complete sense. I mean, of course, you can always relate the two notions, right? Because you always know the distance between your initial state and your Gibbs state. So of course you can apply like a triangle inequality and separate the quantity between what you are saying, like the distance between your state, your initial state and your evolved state, and the distance between your evolved state and the fixed point. So that means essentially that of course if you have information on one quantity, you have information on the other. Maybe not tight because it's a triangle inequality, but you can go in both directions, so whatever. And for the fidelity, I completely agree. The fidelity you can directly relate it to the one norm using this Fuchs-Van de Graaff inequality or whatever. So that means essentially that yes, something similar to this expression here. So yeah, okay, maybe even here. So something similar to this expression here can be written directly for the fidelity, for some function of 1 minus the fidelity, because of course the fidelity being 0, I mean the fidelity being 1 is when the states are the same, and being 0 is when they are different. So it goes like in the opposite direction as this distance. But yeah, all these things have been explored. There are many papers going in this direction. Yeah, I completely agree that that's another very interesting perspective.
Okay.
Yes.
Thank you.
Other question? I have one. If I have well understood, you have the system and you have an environment, and you consider all of them isolated, but there is a weak coupling between system and
Yes.
environment. And I was wondering, because at the very end you have also described the correlation between parts, quantum correlation, and I was wondering if there is some kind of theory of quantum control of the system. I was wondering if you can act over the environment, probably this dichotomical question of if material is candidate or not, taking into account the destruction.
Yes.
Maybe you can moderate this destruction if you are able to modify the style environment and of the environment in such a way that you keep some of the information or make some delay in the destruction of the information of the memory.
Yes, that's a very good question. There are many people working also in this direction. So of course what I'm doing here is just present some mathematical simplification of the problem, I would say, so that we are able to treat it just looking at the system. But there are many people that do actually the opposite, that they say, no, now let's look at the environment, as you're saying, let's change conditions there, let's change the coupling, there's actually a big flow of people nowadays working on non-Markovian models of noise, because they say that Markovian is maybe like too ideal. So what they are starting to observe in labs actually cannot be modeled by this Markovian approximation. Of course, I'm sorry, I'm a mathematician, so I do what is more tractable for us from the mathematical point of view. But yeah, you're completely right. That's something that can be completely done as well.
Thank you. Another question?
So in the last slides, when we started to talk about the initial state, it seems that only is a isolated quantum system. Is that Because
Yes, yes, definitely, yes.
So in such case, you have, I understand you have considered compared to against the internalization of hypothesis. Okay, but anyway, you cannot with your because all the information about the system is encoded in the gamma. And the
Yes,
lambda, right?
yes,
So you can check if having a Hamiltonian because it's closed, you have the whole spectrum.
yes,
And you can check in the spectra if it is closer to a quantum chaos situation or not,
yes,
and see if something which is another question all the time, if having more chaos favors relaxation to your states or not. I mean, I think you can somehow plug in there.
yes. Yeah. So there are actually, yeah, I mean, thanks a lot for the comment. There are actually several things that have to do with that comment there. So first of all, yes, as you say, the Hamiltonian that we are studying here is just a Hamiltonian of the isolated system. But many of the ways to go from here to here actually have to do with relating two different Hamiltonians. So one Hamiltonian is the Hamiltonian of the isolated system, and the other Hamiltonian is a completely artificial Hamiltonian that you construct from the Lindbladian here. So your Lindbladian, in principle, you can write it as a Hamiltonian in a sort of duplicated Hilbert space, something like that, using something that's called the thermophile purification of the state and everything. And then what you do is exactly what you were saying. You compare the spectra of the Hamiltonian of the system with the spectra of the Hamiltonian, the artificial Hamiltonian you have created there, and you can directly obtain information from one in terms of the other and the other way around. So you're completely right, that's something that is hidden behind these arrows. Yes.
Any other questions? Okay, if not the case, we thanks again.